All right, so just one slide background about myself. So I'm a associate professor. I got my PhD from NC State and did my postdoc at NREL. Then do the two assistant research professors at the two energy frontier research centers. One is at the CU Boulder, that's at the Temple. And I became assistant professor at the University of Maine. So now I'm here. So the research in my group, the goal is to design new materials for energy and electronics. Energy includes the energy conversion, like the photovoltaics, which dealing with the converting solar energy directly to electricity, and the photocatalysis, we use solar light to convert, like, for example, to split water into hydrogen and oxygen. And electrocatalysis and thermoelectrics, and also interest in new materials for energy storages, like the batteries and supercapacitors, and also the electronics. Electronics really broad, so I'm interested in new materials for the transistors and the quantum materials for quantum information, and also flexible electronics. So those material can be, you can print it on your skin, and that will be new electronic device. So any new material, I'm really interested into that. So the material discovery here, so traditionally people are talking about, oh, I think early days, which is material discovered by accident or by some type of the intuition or chemical intuition. Then people just study their properties. So this process like takes a long time and very expensive for sure. And the theory usually just like a secondary role. So if you find something you cannot explain, then they ask for a theory for the explanation and to find the reason and the rules, how to control and how to study these properties. Nowadays, I think the last 20 years probably, where people are trying to think about design materials in a new way, like the theory will lead the effort. We use a computer. So if you're given the what type of application or properties, we find the material for you. It's just like playing like the Jeopardy game. So this like here's one example here. But if we use a computer, like now we have supercomputer, we can like calculate material properties. Like for example, here in this figure on the right, this is for water splitting material. Okay, so catalysis. So we can calculate all different properties for 66,000 inorganic compounds, right? So we can calculate thermodynamic stability. Now you can narrow it down, oh, maybe 5,300 is good. Now we calculate the band gap, now narrow down to 11,000. And go down, if we calculate more and more property, basically we can narrow down those material space from a huge number of material to only tens of new materials. So we would just point to experiment, or just synthesize these 50s material for water splitting applications. So different applications like like solar panels, batteries, we know what the properties we have to find, and also the criteria we know to satisfy. The problem is how do we find those material for that? So we use computer, we can help us a lot. So this is in general philosophy for doing material design. And the method here is what method we use. There's so many theory here. So in terms of the length scale and also time scale. So from the top to right, top right to the bottom left, you will see that the time scale becomes smaller time scales, and it's also smaller length scale here. So I think most of the undergrad students, they will see a continuum theory like Newton's law, now discrete dislocation dynamics, molecular dynamics, and the quantum mechanics here. They all have different length scale and also time scale, but of course become more and more complicated as we go to the smaller scales in both time and space. So the method we use based on quantum mechanics. So we're really dealing with the nanomaterials, understand the materials at the atomic level. So that's what we call density function theory. That's the main method we use. Okay, so I just now to give you 3 examples of my ongoing research. One is about high entropy 2D layered materials. So 2D material, 2-dimensional materials. Probably you know that, which is the graphene. let's see if we can use my, do you see my mouse moving?
Yes.
Okay, so like the graphene here, you will see, right? So it contains one element, boron, carbon nitride, transition metal, chalcogenize. So all those 2D materials, they have a lot of energy applications, including lithium-ion batteries, sodium batteries, and also supercapacitors. So there are also other type of the applications on that. So you will see the common features of those two-dimensional materials. They have only one or two elements, right? For graphene, only one element. Carbon nitride has two elements. Transition metals also they also has the two elements of that. So idea here we are trying to do is to put more elements together to see if we can form a new type of the layered 2D materials. That's why we call high entropy 2D materials. So this is the first study. This is the first proposal. My first proposal to get funding from the BES Department of Energy. So we're trying to design these new materials for energy applications. So it involves a lot of applications. I think this is the application, the collaboration between University of Maine at that time and also Oak Ridge National Lab. So I'm the PI for this project. I have one postdoc who is doing the materials prediction. And if we predict some new material, we ask the experimental collaborators, which is Ying Chao Yang from also University of Maine. They do material growth to verify all our newly predicted material, whether they're synthesized or not. And we have very good success on that. And he has one PhD student working on this. So after this material synthesized, they characterize those material properties like structures, and also they study why this material would be good for supercapacitors, for example, and the batteries. A lot of the facilities here were not available at the university level. We don't have really high TM, STM, those facilities. They're so expensive. And so we have samples brought to that. So one attractive thing is we try to train also students and postdocs at least each year, 1 or 2 months at the national lab of there. But because of a pandemic, so they never happened. But anyway, so this is the one project we are still working on. Um, the second one is also about the plastic halide. So this is about the PV solar cell material. So there are three generations of solar cells. One is silicon, the other one is thin film, the third one is multi-junction or PV of that. So in terms of the efficiency and the cost, you can see clearly from this figure here. So we are working on, I think the current here, people mostly working on the thin film sources. So there's still some commercial materials like the cadmium tellurides and the copper indium gallium diselenide, so CIGS, sometimes people call that. But these two materials commercialized, but they are toxic, so it's really not good for massive applications. There's newly discovered material, which is a perovskite halide. This is the hybrid perovskite halide here. This is a very hot material here. So the efficiency is really, really high. But the problem now we are facing is they're so unstable. So what's the reason behind this stability here? So that's the main focus of this project. We're trying to understand why this material is so unstable and how to mitigate this instability. So then we come up with the idea of the high entropy, the perovskite materials, right? So this material here, this project also involves collaborations with some experimentalists. One is from the UMaine here. He's doing the understanding the stability and evaluation analysis, and also involve the synthesis and property characterization from Arizona State University here. So this is a new type of material here, which is instead of focusing on 1 or 2 metal elements, we put the 4 or 5 metal elements and see if we can have a lot of more more versatile or more stable compounds. So those new compounds may have a lot of potential optoelectronic applications. One like the thin film solar cell, which is one actually. So there are a lot of others I just listed here, but it's still very, very hot research area. Okay, so the third one is just the also NSF. It's about the studying the solid state phase transition. So everything is about phase transitions, right? So the memories. I think these are 0, 1, 0, 1 is about phase. So for solid here, one like they have usually like one material, they have many different phases like the diamond and graphene, like shown here, right? So those two material here, so how can we control and understand? They have the same elements, but they have complete different structures. Those different structures, they have very different properties. If we know how to control those different phases and make one phase transfer to another phase very easily, that's a big step. For example, like the graphene carbon, right? If we know how to convert one material to another, now you can make it maybe a lot of the diamonds from the graphene, right? Or graphite. Now you will become really rich if you can do that. But the fundamental, the huge kinetic barrier. So we really historically, so it's really hard to understand what's the kinetics behind that. So we're trying to understand this kind of kinetics between many type of the important solid phase transitions. Hopefully we can find some rules or design principles to help experimentalists to control those phase transitions. Then we can find some lot of applications on that. Okay, so these are three ongoing research projects. So in the future here, I have a number of topics in my mind. So these are just list here, 6 of them. So each one has some ideas on that, but I'm really looking into some collaborations here or outside the campus. One is we're trying to do is to developing the transformative, the new machine learning methods to speed up the material design. So right now we're using quantum mechanics. That's the mainstream, still the main paradigm. It's too slow right now. So there's so many data have been generated so far. So how can we make use of those data and make a machine learning algorithm to help us really speed up the material discovery? That's the one main focus. I will try to focus. The second one is I'm really interested in like hopefully we're working on some wide gap semiconductors. We are interested in like electronic, optical, and defect properties of that. So that is the maybe related more to a semiconductor initiative. Into material classes, I'm also interested in like the 2D materials and the heterogeneous structures and the new materials for single photon emissions. Particularly, I'm also into the surface interface materials. So that will be a new area. So and also property. So there's any material they have different properties. How those different properties couple each other. Okay, that's maybe we can get some very new and advanced materials on that. So this just like some really rough, very general ideas. So really open to any discussion on that. Thank you, and open for your question.